importance of reunion. I know the charm associated with the reunion, and but I really do not know whether on the day of reunion, whether one really wants to hear Stephen Hawking. I mean, that's a bit too much, I believe. People would like to enjoy sing songs and other things. So I'll try to explain to you the work of Stephen Hawking the way I understand it. But before anything, may I ask you that you want me to speak in English or Bengali? But is there anybody in the audience who cannot follow Bengali? There is somebody, but then I should not, because then that person will be left out. Okay, so if you want to ask me a question in Bengali, that part is fine. So, I mean, of course, I can see your very, very well-known teachers of this university. I have the really great fortune once to be associated with this university in the physics department, and I know all of them. They are very well-known scholars, and I am pretty sure that all of you are very good students. This is probably one of the best students in the country, the best university in the country, and very well-known department. So even in my institute, I know that this department is rated very high in the ICS. So Hawking space-time, some hidden wonders. Can you remove this mouse cursor from the? Yes. So please, without hesitation, stop me and ask me questions in English or Bengali, in whatever language you want. You do not have to wait till the end. Any point you don't understand, please ask me questions. So, we live in a universe. This universe is incredibly large. And just to give you an idea, that you know that Sun is our nearest star, about which we are rotating, the planet Earth. And if Sun is a very typical star, the size is very average star, and in universe there are cluster of stars form a galaxy. And in our galaxy, which is called Milky Way, there are 10 to the power 11 number of stars. That is, put 11 zeros after 1, this number of stars, and Sun is just one of them. Then there is some empty vacuum. Then there is again another cluster of stars forming another galaxy. And each galaxy approximately contains same number of stars, approximately about 10 to the power 11 or 12. And then we have counted that there are approximately 10 to the power 11 number of galaxies. And the distance between any two galaxies, average distance is 10 to the power 18 kilometers. Put 18 zeros after 1. And any two galaxy, and then there are 10 to the power 11 such galaxies. And we are in one such galaxy, in one such star and one planet. We are not even a point in the universe, but we are really trying to understand the universe. So probably this is one of the most ambitious things that one can imagine. And Stephen Hawking contributed in understanding our universe. What can be a better thing than this? But one thing is certain, that if you want to understand Stephen Hawking, his real importance of his work, you have to understand Einstein. Without Einstein, Stephen Hawking couldn't stand. So let me briefly tell you about Einstein's contribution so that you can really appreciate Stephen Hawking's contribution. So, about our universe, our common sense notion is that our universe is embedded in a three-dimensional space, that all of you know that we live in a three-dimensional length, breadth and height. And we evolve forward with time. Time is something which takes us towards the future, following the Newton's laws of motion. So that is our first fundamental understanding of nature. Now, all of you, I am sure, will agree with this statement. Question is that what are the characters of the space where we live, and exactly what do we mean by time? Now, see, space, we have roughly a feeling that this space we are kind of moving around, really without being much bothered about what is this. We feel a sense of emptiness in the space. And time is something which, once we look into our watch, we see something is ticking forward. And then we prefer to forget it because we really don't want to think about it. But this time and space are very, very important things to understand if you really want to understand the modern science. Now, we can say roughly that Newton's law of motion, all of you know that this force is mass into acceleration, a very simple looking law, but this law was incredible because you can imagine this entire law tells you that whatever be the material body around you, whether it is you or sun or anything, the car on the street or a raindrop or anything, this equation tells you that how its motion will be governed by a force and how it will accelerate. So it unifies the whole material world into a single equation. So this is probably the first and probably the greatest unification that the world has ever seen. So in this sense, Isaac Newton is probably our father of science all time. Now this law has a deep meaning. We say the force, the left-hand side force, is the cause of all changes of dynamism in nature. Without force, everything will be static, will remain static. Force actually makes things move. And there are basically two main forces. One force is called electromagnetic, the force which is the force between two charges, electric charges or current, the electromagnetic force, and the force of gravitation, that anything you lift from your hand, it will go down, mass attracts another mass. Now why I say these are the two main forces, because these are the two forces which actually controlling everything that you see around you. So it includes not only the apple falling from the sky, but suppose you are pushing it by your hand. This is an electromagnetic force because the electric charges in the atom in your hand, the skin, they are coming close to the electric charges of the wall of this bottle, and then everything composed of electric charges, because everything composed of atoms and molecules, and they repel each other, therefore it is going in that direction, and my hand is receiving a force in the opposite direction, and everything that is happening around you, when you stand up from your chair, you will push the handle of your chair, is once again an electromagnetic force. So electromagnetic force is all around, and apart from that, there is another force called gravitation, the force between masses. So these two forces essentially control everything in nature, and therefore we focus into these two forces properly. Now in the right hand side there is a term, so this is about F. M is the object which is moving, and acceleration is given by the second rate of derivative of space x, y, z. So we live in a three-dimensional space given by three coordinates x, y and z. And t is that mysterious time which measures that how the position changes with time is velocity, and how velocity changes with time is acceleration. So now you can see that basically this x, y, z describes a three-dimensional space and t is the time. So we can say that we live in a universe where all natural phenomena is a kind of three-dimensional cinema, where this screen of the cinema is the space and t is the time with which the cinema moves towards the future story. And one need not to go to a cinema hall and wear a spec to a 3D movie. You just stand inside the nature, and nature is the most beautiful 3D movie which is happening 24/7, following the law of Newton. So this is the law of the cinema. Now, Newton said, according to Newton, time is universal and unique for all events. That is, anything is happening, there is, as if something like this, that there is one clock in the sky, and all of us, everywhere, is looking at that clock. And at that clock, suppose there is a time now 2:45 or something like that, 2:50, and then we see everywhere, and here we are talking, somebody in the United States is sleeping, somebody is playing cricket in somewhere. So everything happening with respect to this clock, this universal time, which is taking us towards the future, and there's one time for all of us. For this reason, when we write Newton's law for two different objects, we take for mass m1, m2, So the position x1, y1, z1 is the position of one particle, x2, y2, z2 is the position of the other particle. But we never take t1 and t2. We always write t. So d2 x1 dt square is the acceleration of number one particle. d2 x2 dt square is the acceleration of number two particle. His coordinate are different, his mass are different, force is different, but t is same. So this is the Newtonian assumption of universal time. We never write t1 and t2. And also, space about space, Newton thought is a three-dimensional space, of course, infinitely extended, and the geometry of the space is Euclidean. Now, geometry of the space means, all of you have studied your class 4, 5, maybe Euclid geometry, which tells you that if you take any 2 points, find the distance between them. The shortest distance is a straight line. All the other distances are curved line. So this is the fundamental assumption or axiom of Euclid, that shortest distance is a straight line between 2 points. You will say that that is of course true for always. I mean, is there any possibility that shortest distance is not a straight line? The answer is yes. There is such a possibility, and which I will now demonstrate to you. That if you have consider this two-dimensional surface, and this shortest distance is a straight line, you connect this to the straight line. But suppose you curve it. If you curve it like this, if you curve it like this curved surface, then the shortest distance now along the surface is a curved line, because you are seeing a curved surface. So the curved surface is a curved line. So the shortest, there is no straight line on a curved surface. Consider bent paper. There is any 2 points. If you have to confine within the paper, you cannot have any straight line. It's always a curved line. But Newton thought that our space, three-dimensional space, is always follow Euclidean geometry, and he said in the first law portion that every body without any force moves in a straight line in uniform motion. So he assumed straight line. Now, Einstein basically questioned Newtonian view about space and time. He didn't do anything else. So, in other words, theory of relativity is theory of space and time, nothing else. So, what did he do actually? He questioned the Newtonian view about space and time. He said that, see a strange observation. Suppose there are 2 objects A and B, and these are observer. This object moves with velocity v1 in this direction. That means with respect to this observer, this travels the distance v1 in unit time, and this b travels the distance v2 in unit time as this observer sees. Now suppose you ask that what is the speed of b as observed by A. Now you will see that a person A, he is traveling v1 in unit time with respect to him, this v2 in unit time with respect to him. Then in unit time the distance between them has been reduced by v1 plus v2. The distance is reduced by v1 plus v2. So this man will say that b is coming towards b with speed v1 plus v2. So which is called the relative velocity. So when you sit in a train, another train coming from opposite direction, it appears that it's traveling much faster because you are standing in a moving frame and it appears moving very, very fast. So we learn, according to Newton's law, the relative velocity, that according to relative velocity of b, that is b, as observed by A, is v1 plus v2. This is the prediction of Newton's law. But this law, this so obvious law, v1 and v2 distance is getting reduced by v1 plus v2, faced a serious drawback. Drawback is, suppose this b, instead of moving with velocity v2, it is moving with speed of light. Suppose it is traveling with speed c, which is very, very high. All of you know speed of light is 3 to 10 to the power 8 meter per second. Fine. So speed of light as observed by the observer 3 to 10 to the power 8, and he travelled the distance v1. So the relative velocity should have been v1 plus 3 to 10 to the power 8, the speed of light. That was the prediction. Speed of light, then with respect to the observer, the relative velocity of light with respect to A should have been v1 plus c, but strangely it is still equal to c. So what I am saying, that this observer also saying that it is travelling with speed of light c, the static observer saying this is travelling with speed c. Now this is such a, terrible observation, because clearly the distance he travels in unit time v1 and he travels c, the distance between them has been reduced by v1 plus c. So how is it possible that this observer is still saying that he is traveling with speed c? Speed of light is not changing. When you are static, c. When you are moving, still c. So Einstein said that this thing has only one resolution. Otherwise you cannot explain. The distance is actually getting reduced by v1 plus c. How is it possible that you are seeing it c? So if a train of opposite direction comes with speed c, then your velocity, when you are in a moving frame, you will see c. It's not changing. Einstein said this can only be explained if you do the following. When this man is saying this is moving with v1 in unit time, this is moving c in unit time, and you are asking how much is the speed of b as observed by a in unit time, how much distance you travel, you are assuming the unit time in this frame and this frame are identical. The time is moving identically. But suppose the time doesn't move identically. Suppose this man's clock and this moving man's clock runs differently. Then what will happen? Then, since speed is distance by time, if the time gets bigger in a fraction, if the denominator becomes bigger, then effectively it becomes smaller. So you can do a back of the envelope simple back calculation that how the time in the two frames should be related so that the speed, the relative speed still remains c. So we put c, forcefully assume the times are different and calculate what is the relation. The relation that we find is a one-line calculation that the flow of time depends on velocity is the following relation. Now this tells you that t0 is the moving time, you say 1 second in this man's frame, and t is the 1 second in this moving man's A's frame, and t is the velocity of A, suppose. That they are related like this. In other words, since v is non-zero, this is a quantity which is less than 1 of course, but 1 minus a quantity is less than 1, fraction is even less than 1, so t is greater than t0. So time is dilated, that is moving clock is running slow. His 1 second has become his 5 seconds, so he is running much slower. So it is moving very slowly. So within the time interval which is showing 1 second is taking much bigger time before that. So moving clocks run slow. And don't think that I am telling you some fantasy story. It has been tested even experimentally that even cell division becomes slower if you put something in a very high speed way. But now the question is that if v is in normal light, v is much less than the speed of light. We never move with speed of light. So this quantity is relatively small. It's a very small quantity. So t equal to t0, then it is Newtonian universal time that all times are same. So as long as you are moving with slow speed, you can this Newtonian time is a good approximation. But as your speed increases, Newtonian time breaks down, and the time interval becomes different in different frames. Your clock will be different from my frame. So previously we thought that I can identify your coordinate as x1, y1, z1, your coordinate as x2, y2, z2, but t are identical for all of us. But now I understand that for each of us we have different time. So we do not live in a three-dimensional space, we live in a four-dimensional space and time. Any event has to be, you have to be described by 4 coordinates, not only by 3 coordinates. So that led to, so time is not universal, just as everything has their own position, each of them has their own time. Time is like a coordinate, and flow of time is relative. So led to the idea of four-dimensional space-time to describe an event x, y, z, t. Now, with this idea, Einstein put forward an absolutely fantastic concept. The concept is the following. He said that there is a connection between geometry and force. Now, this idea, nobody knows how it came to his mind. He was a genius, so it is very difficult to understand how a genius mind functions. So he said that force is a wrong concept. Whatever we are used to for so many years, there is nothing called force. It is basically geometry. So what did he say? He said that Newton said that the apple is falling from the tree because of force of gravitation. And he was such a genius, he also said that the same force is responsible for the motion of the planet around the sun. They are attracting towards the sun and they are rotating the same gravitational. And he said that this force is given by a simple law that if you have two masses m and n, this force of attraction between them is given by this equation, which is g by r square. And now it turns out experimentally that G has such a small value, this is called constant, this is called universal constant of Newton, gravitational constant. This value is so small that unless a mass is very large, or both the masses or at least one mass very large, this force is negligibly small. And for this reason, you are sitting here, you are sitting here, you are attracting each other, but you are not colliding into each other. Why you are not doing? Because the gravitational force is too small to overcome the frictional force, which is an electromagnetic. So these two objects are not crashing into each other, though they are attracting because they are being stopped by friction. Now, but if one of the mass, say, I'm leaving, this is going down, because at least one mass, maybe Earth has a huge mass, or Sun and mass. So whenever the masses are large, then the gravitation becomes very, very important. So instead of Newtonian concept of this action at a distance, but Newton, the way he portrayed gravity, Einstein came out with a brilliant idea. This idea is absolutely tremendous. This idea tells you, can I have this paper, just one sheet of paper? Can you just, if any of you give me, do you have? Just one sheet of paper. Or if you don't have, is there anything here? Thank you. Now, what Einstein said is the following. He said that all of you know that in an Euclidean flat space, shortest distance between 2 points is straight line. Sum of the angles of a triangle is 180 degrees. The circumference of a circle is 2 pi r. This we all know. But do you know this law fails completely if you consider a curved circle? On the surface of a sphere, if you draw a triangle and you draw 3 tangents here, so draw a triangle like this, the sum of the 3 angles is greater than 180. If the surface instead of being convex, it is concave, then it is less than 180. And if it is flat, which you have learned, then it is 180. Now, and of course the shortest distance on the 2 points on the surface is of course not a straight line. There is no straight line on the surface of a ball. Where is straight line? So what you do, what Einstein said, that Newton's idea is that space-time is flat, space-time is like this flat. A body travels along the shortest path, that is straight line in absence of force. So when there is no force, a body travels the shortest path, that is straight line. 1 Newton said. And when accelerates when there is force, and acceleration means it is the velocity is changing, it's a curved path. So what Newton said, that straight line, no force, in presence of force it's attracting, it's a curved line, it's accelerating. So Einstein said that if this is the sun and this is the earth, sun is attracting the earth which is traveling in a curved path. The path is elliptical, however the curve is path, so there is acceleration because there is a force by the bigger object to the smaller object, therefore it is attracting. Einstein said, no, this sun is never attracting the earth, in fact there is nothing called force. Instead, what this sun has done, this sun has bent this space like this. And on a space which is curved, the one body has to travel in a curved path because there is no straight path. Space is curved. And you have to travel along a curved path. And as a result, seeing the path is curved, you are thinking that there is acceleration and there is force. So force is an illusion. So a mass doesn't attract another mass. A mass changes the geometry. And the geometry getting curved, you have no option but to travel in the curved path. And seeing the curved path, you are thinking that there is an acceleration and therefore there is force. So he said, presence of mass energy curves the space and time because we are living in a 4-dimensional space-time. The shortest distance is now a curved line because there is no straight line. There is no straight line on this. See, this is curved, there is no straight line. any point, 2 points are carved line. And this gives the illusion of acceleration and hence the existence of force. So illusion of force originates from. Now this is such a revolutionary concept, throwing away the concept of force by the geometry. So people asked Einstein that, okay, this sounds very impressive, but the question is that Newton said a mass attracts another mass. Fine. You have replaced it by saying that the mass curves the geometry. Now my question is, why a mass curves the geometry? Suppose you ask this question. Why it changes the geometry? Then Einstein said something very deep. He said that, see, if I ask you that what is the definition of mass, you have to answer. In Newtonian formulation, mass cannot be defined. And you should remember, whenever you taught in your books, what is the mass, you have no answer. Sometimes you say the amount of matter in a body. This has no meaning. Then if I'll ask you what is matter, then you will say amount of mass in a body. So the question is, mass is an ill-defined concept. We have some intuitive idea. We can compare in a weighing machine to objects, how the earth is attracting, this kind of thing. And we have defined by dividing by gravitation g small g, I call it a mass, but these are all very artificial concepts. There is no conclusive definition of mass. If you say Newton's first law, force is mass into acceleration, mass is not defined because an equation, acceleration is defined, rate of change of velocity, but what is force? If you say force is mass into acceleration, then I just ask you what is mass. If you say mass is force by acceleration, then I ask you what is force. Single equation cannot define two things. So mass is an ill-defined concept. So Einstein says in the first time I gave a definition of mass. Mass is something that changes the geometry from flat material to curved non-material. This is the first definition of mass. So you cannot ask the question why mass has changed the geometry. This is the definition of mass. Mass is a property by which it changes the geometry. This is a very conclusive, correct definition. Now, then what happened? Einstein was taught by his friend Marcel Grossman by some very basic mathematics of curved geometry. What it is? He said, I am telling you some brief idea. So suppose x, y, z is a coordinate, and x plus dx, y plus dy, z plus dz are 2 points separated by a small distance. What is the distance square? This is the distance. Right? D square is dx square plus dy square plus d square. It's a Cartesian coordinate geometry. You learn x2 minus x1 whole square plus y2 minus y square plus z2 minus z1 whole square is the distance. But this formula is wrong for a curved geometry. It doesn't work. For a curved geometry, the distance between these 2 points will be, this was 1 into dx square because this 2 minus this 1 into dy square, 1 into dz square. But if the geometry is curved like this, you take 2 points intrinsically separated, then the distance between them will be 1 plus some function of x, y, z dx square, 1 plus some function of x, y, z dy square, 1 plus some function of x, y, z dz square. This coefficient will no longer be 1 to 1 to 1. This deviation from 1 measures the curvature. And this quantity has a name in mathematics called metric of the space. So these are the metric of the space which defines the curvature of the space. Now mathematicians formulated it earlier by a mathematician called Riemann. It's called Riemannian geometry. So what it is, so you have to test the distance between 2 points, which is 1 into dx square, 1 into dy square, 1 into d square. If not, there is somehow something else, the space is curved. That's it. Now, these coefficients are called metric of the space and determine whether the space is flat or curved. Now, we know we are working in 4 dimensions because Einstein taught us. So it has to be 1 plus f1 dx square, 1 plus f dy square, 1 plus f dz square, so distance in 4 dimensions, and 1 plus f4 dt square. It's a natural extension because 3 coordinates are 4 coordinates, but instead of plus there is a minus. Now this minus sign is because there is one difference, though time is, you have your time, you have